Hello. Today, we're diving into image classification using convolutional neural networks, or CNNs, with TensorFlow. This fundamental computer vision task allows models to identify objects, forming the basis for many modern AI applications. Image classification is a core task in computer vision, where models learn to identify and categorize objects within images. It's about training a digital brain to distinguish between different subjects, like recognizing a cat versus a dog, or various types of vehicles. CNNs are powerful because they use convolutional layers to automatically detect features like edges and textures. These layers intelligently identify basic elements, progressively building up to more complex patterns and shapes for robust image understanding. Let's build a CNN model in TensorFlow. First, prepare your dataset, which serves as the training ground. A good example is the SAFAR 10 dataset, containing 10 distinct classes of objects like airplanes, cars, and animals for diverse learning. Use Keras, TensorFlow's high-level API, to create the model. The initial step involves importing necessary libraries from TensorFlow Import Keras. This grants access to Keras's powerful tools for constructing and training neural networks efficiently. Define the model with CONV2D layers for feature extraction, capturing patterns. Max pooling 2D layers reduce spatial dimensions, decreasing computational load. Flatten layers convert feature maps into a 1D vector, feeding into dense layers for final classification. Compile with Atom Optimizer and categorical cross-entropy loss. This configures the learning process, where the Atom Optimizer efficiently adjusts model weights. The categorical cross-entropy loss function quantifies error, guiding the model to minimize discrepancies. Now, train the model on your dataset. During training, the model iteratively learns, adjusting parameters to recognize patterns. After training, evaluate its performance and accuracy using a separate test dataset for an unbiased assessment of generalization. Use model.evaluate to get metrics like accuracy, precision, and recall. Accuracy measures overall correctness. Precision indicates true positive predictions among all positives. Recall shows true positive predictions among all actual positives, offering nuanced understanding. For example, if accuracy is 85%, that's solid, but check confusion matrices to see misclassifications. These matrices provide a detailed breakdown of correct and incorrect classifications for each class, pinpointing where errors frequently occur. To optimize, try data augmentation to prevent overfitting, where models perform well on training data but poorly on new data. This involves expanding the dataset by applying random transformations like rotating or flipping images, making the model more robust. Add dropout layers, which randomly deactivate neurons during training, forcing the network to learn robust features. Or use transfer learning with pre-trained models like VGG16. These models have learned rich feature representations, allowing fine-tuning for specific tasks. Experiment with hyperparameters like learning rate, which dictates the step size for weight updates. This profoundly impacts training stability and convergence. By carefully tuning these and applying optimization steps, your CNN can achieve higher accuracy and generalization. Thanks for watching this exploration of image classification with CNNs and TensorFlow. We hope this overview provided valuable insights. We encourage you to try implementing these concepts yourself, experiment with different datasets, and discover deep learning's incredible potential.